In subtopic 7.2 on nuclear reactions, you'll notice so far we haven't really looked at nuclear reactions. We've been looking at binding energy. We're now going to start looking at those, and we needed to sort of do binding energy first to make more sense of these nuclear reactions. The first nuclear reaction that we're going to look at is nuclear fusion. And as the name suggests, if you fuse something, that means you're joining it together. So fusion is the joining of two small nuclei to form a larger nucleus. Sometimes in that process you'll also form some other byproducts. We're not going to really worry too much about those byproducts. We're just looking at the fact that if we take something smaller, or two parts that are smaller and join them together, we'll end up with something larger. As an example, so imagine that we have this nucleus of hydrogen 2, so that would be 21H, and we're going to fuse that with a hydrogen 1, so otherwise known as a proton. So both of those are going to be sort of smashed together, and out of that we see that we'll get a different product that is a combination of those two nuclei. So in this case, fairly straightforward, we'll have two protons and one neutron, and so that means that we've now formed 32He. The nuclear reaction for that is just a case of writing those reactants and showing the product there as well. So again, you'll notice here that the atomic number and the mass number are balanced. You could also write on here that there is energy that's released, but we'll talk about the energy in a second. Before we go into that energy though, need to specify here that in order for fusion to occur, high temperatures and spell that correctly, high temperatures and pressures are needed. And the reason for that is that if you think about that situation that we just talked about, we've got two particles that have protons in them, and so we need those high temperatures and pressures to overcome electrostatic repulsion. Now on Earth, those conditions, we haven't been able to produce them in a controlled manner, so we haven't been able to use fusion in nuclear power plants, but we have been able to use it for a fairly destructive purpose in the case of a hydrogen bomb. So by fusing hydrogen atoms together, hydrogen nuclei together, we can release a lot of energy and cause a lot of destruction. The other thing that's important to note about fusion is that it's what occurs in stars. So our sun is basically a fusion reactor where we have a lot of energy being released from each of those fusion reactions. Now, the product nucleus that we see in this situation is usually going to have a higher binding energy per nucleon. So that means that what we produce has a greater stability, I suppose, well, not necessarily stability, greater amount of energy per nucleon that's keeping it together. You'll notice too that on the binding energy per nucleon graph, anything that's larger than iron, so anything that's sort of past the peak, won't usually tend to fuse together, because that would mean that if you have two smaller things joining to something larger, the binding energy per nucleon will decrease. That means that energy would need to be added to that reaction, and so we don't usually see that occurring. It does happen in the universe when a supernova occurs, so an explosion of a star. There's extremely high temperatures and pressures there, and so those heavier elements can be formed. So you can basically think of anything that's made up of larger elements is basically the product of a star explosion. So we're sort of all essentially stardust. Now, while we're talking about the binding energy, we also should really talk about the mass. So the mass of the product nucleus, you might be able to guess where this is going, given that energy is released. So the mass of the product nucleus is less than the sum of the two reactant nuclei. So it's a similar situation to the calculation that we did for binding energy, and we end up with energy being produced, and so the difference in those two masses is released as kinetic energy of the product. So that means that the product is going to be moving fairly quickly. So to give you a bit of a sense of what's happening in this situation, we'll have a look at that equation that we just dealt with above. So if we consider the mass of the hydrogen 1, now it might look a bit odd here that we have slightly more than the mass of a proton. That's because we're including the mass of the electron here, given that it'll be moving along with the proton. Mass of hydrogen 2 is 2.014101 atomic mass units, and the mass of the helium 3 that's produced is 3.016029 atomic mass units. Now if you find the difference in mass in that case, I'm not going to write out the full calculation. You can see we're basically taking the sum of the top two and subtracting the bottom one from it. We'd end up with a value of 0.005897 atomic mass units. And if we use our shortcut calculation to figure out what the energy is, so multiplying that amount of mass in atomic mass units by 931.5 mega electron volts, we get a value of 5.493 mega electron volts. So in that one fusion of helium 1 and helium 2, we end up with 5.493 mega electron volts being released. Doesn't seem like all that much, but if you were to combine a whole lot of the hydrogen 1 and hydrogen 2, as happens in the sun every day, that amount of energy starts to add up quite quickly and would release quite a large amount of energy. We'll look at a few more example scenarios in class. We'll actually look at the chain of reactions that occur in the sun and a few other different reactions that occur in different stars to give you a better sense of some of the other nuclear fusion reactions that happen in stars and in our own sun.